Here's a simple mnemonic device that I use to help work with series circuits and parallel circuits. It's called SIC PVC, and it goes like this. In a series circuit, current is constant. In a parallel circuit, voltage is constant. Let's look at some examples using simulations.
Take a look at this circuit. What kind of circuit is that? It's a series circuit. How do we know it's a series circuit? Well, if you look at these electrons as they pass through the entire circuit, you see that there's only one path to follow. There's no branches, only one path. They have to go through each resistor one after the other. Series, just like a TV series, one after the other. So what's special about a series circuit? Well, current is the same everywhere because the flow is the same everywhere. Using my ammeter right here, I can hold it over and see a current of 0.67 amps that remains constant through every part of the circuit. So in a series circuit, current is constant. However, voltage is not constant. Some voltage is lost at every resistor in this series circuit, where the magnitude of the voltage at the battery is 20 volts. If we take the voltage at the first resistor, we see the voltage is 6.67 volts. For the second resistor, 6.67 volts. And for the third resistor, 6.67 volts. Because these resistors are all the same value, that 20 volts is split up evenly between them. However, if one of those resistances were changed, things would be different. As you can see here, I've changed the middle resistor to 30 ohms. We see the battery still has a voltage of 20 volts, but now that voltage will be split up differently. For the first resistor, it receives a voltage of 4 volts. The middle resistor, 12 volts. And the final resistor, 4 volts. And of course, current will still be the same value throughout the circuit, less than before because now we have more total resistance, 0.4 amps, everywhere. In a series circuit, current is constant.
Let's take a look at this one, and instead of simulating it, we'll do all the calculations by hand. Here we have 3 resistors in series, so we'll be using SIC. In a series circuit, current is constant. And before I get into all of the math, I want to set up a triangle for each component. I found it quite helpful. So here I have my Ohm's law triangle for the battery, and then I'll put one for each resistor. I can put in the values that I know. For the battery, for example, I know that we have a voltage of 24 volts. And for each resistor, I can put in the resistance values as seen in the picture. So in a series circuit, current is constant. Well, the first thing we have to do is find the total resistance. Remember, to find the total resistance in a series circuit, we simply add up the individual resistances. 4 plus 6 plus 2 would give us a total resistance of 12, and that would be the resistance for the entire circuit, and I would describe that at the battery. That's not the resistance of the battery, but merely the total resistance of the circuit that the battery has to push. From here, we can calculate the total current at the battery as 2 amps. 24 over 12 is 2. Now is where we use SIC, series current constant. Since the current is known at one location, we know that that same current will exist at every location through every resistor. 2 amps through the first resistor, 2 amps through the next, and 2 amps through the last. We can now use multiplication to find our individual voltage values for each resistor. So we would have 8, 12, and 4. In this circuit, current is constant, and the voltages should add up to our total voltage. We look at those. 8 plus 12 is 20, plus 4 is 24. Does it match? Absolutely.
In this next example, we have a different circuit. What kind of circuit is this? It's a parallel circuit. We have 2 resistors in parallel. How do I know they're in parallel? Well, this little part of the circuit right here, you can see the electrons are splitting up and either going one way or the other. It's like a fork in the road. And then over here, we have another junction where those electrons come back together on a single path. The electrons are going really fast through the battery, and then they're being split up and going through each resistor, depending on which way they go. In a parallel circuit, voltage is constant everywhere. So if I look at the voltage at the battery, we measure 20 volts. However, whenever I measure the voltage at the 10 ohm resistor, it's also 20 volts. Notice how it says negative 20, but if I just switch the order, it says positive 20. Either way, I would report that as 20 volts. And then at the 5 ohm resistor, again 20 volts. Same voltage everywhere in a parallel circuit. But current is different. I see the current at the battery is 6 amps. Current represents the flow of the electrons, and that flow gets split up at this first three-way junction. Through the upper branch, through the 5 ohm resistor, we have 4 amps, and through the lower resistor, we have 2 amps. Why do you think we have more current through the smaller resistor? Because it has less resistance. 10 ohms is more resistance, so it doesn't let as much through. 2 amps and 4 amps come together to give us our 6 amps that goes through the battery. In a parallel circuit, voltage is constant.
In this last example, we have 2 resistors in parallel connected to a 12-volt battery. Which mnemonic do we use? PVC. In a parallel circuit, voltage is constant. So we should expect that if we have a 12-volt battery, that each of those resistors will also fill 12 volts of potential difference. I'm going to start off again by bringing my triangles in for each component, for the battery, for the 6 ohm resistor, and then for the 12 ohm resistor. I can now type in or write in my given values for the battery of 12 volts. And I know the resistance of each resistor, 6 and 12. And because PVC says parallel circuit, voltage is constant, if the battery gives 12 volts, then each resistor individually will have 12 volts. For each resistor now, I can calculate the individual current. For the upper resistor, the 6 ohm, we would see a current of 2 amps. And for the lower resistor, we would see a current of 1 amp. Those currents must add up together at the junction to give us a total current of 3 amps through the battery, which means that the total resistance of the circuit would be 4 ohms. Let's double check that by finding the resistance of the 2 resistors combined in parallel. So for this one, we would have to say R total equals 1 over 1/6 plus 1/12. I can find a common denominator within the larger denominator, and this turns into 1 over 2/12 plus 1/12. Combining those two terms, I have 1 over 3/12. Flip it to see 12 over 3, which reduces to 4 ohms.
I think we're right. Thank you very much.